Now, in this part, we will discuss another part of parametric differentiation where we will find the second derivative of parametric differentiation. So, for second derivative of parametric differentiation, let's say we have the same situation. If our x equation is in term of t and our y equation also in term of t. So, for the second derivative, for usual function, we just have to differentiate our first derivative, which in this case is dy dx. But this is not the case for parametric, because basically for dy dx, we still have to differentiate this with respect to t, because our final answer for dy dx still in term of t. So, to counterback this situation, in order to find the second derivative, we have to multiply with dt over dx. So, we can also rewrite this as the d over dt of dy over dx divided by dx over dt. Let's do some exercise to check our understanding. So, example 18, part A, we have to find the second derivative when our x is equal to exponent to the power of t and our y is 60. So, we don't have any other choice but to find the first derivative first. So, for our x equation, we will have dx over dt equal to exponent to the power of t. And our dy over dt, in this case, we just have to differentiate 60, so we will get 6. Means that our dy over dx following our chain rule is dy over dt times with dt over dx. And in this case, this will be equal to 6 times with 1 over exponent to the power of t, and our final answer here will be 6 exponent to the power of negative t. Now, in order to find our second derivative, we have two main steps. Step 1, we have to differentiate our first derivative first. So, d over dt, because we have to differentiate it with respect to t, of our first derivative, dy over dx, in this case means that we want to differentiate our 6 exponent to the power of negative t. And in this case, we will get negative 6 exponent to the power of negative t. Now, step number 2, we have to substitute this into our chain rule. So, basically, the chain rule for the second derivative will be equal to d over dt of our first derivative, dy over dx, times with dt over dx. So, we just substitute everything. So, this will be equal to negative 6 exponent to the power of negative t times with 1 over exponent to the power of t. So, our final answer here would be equal to negative 6 exponent to the power of negative 2t. And that is how you find the second derivative by using parametric differentiation. Let's do another example. So, for this situation, we have our x equal to t cubed minus t and our y is 8 minus 2t. So, for first part, same as before, we find the first derivative for our x equation. So, in this case, our dx over dt will be equal to 3t squared minus 1. And for our y equation, our dy over dt in this case will be equal to negative 2. So, following our chain rule, our dy over dx will be equal to negative 2 times with 1 over 3t squared minus 1. And in this case, our final answer for first derivative would be equal to negative 2 divided by 3t squared minus 1. Now, in order to find the second derivative, we have to, step number 1, differentiate first our first derivative with respect to t. So, d over dt of negative 2 divided by 3t squared minus 1. For this one, we have to apply power rule. So we have to differentiate basically negative 2 times with 3t squared minus 1 to the power of negative 1. Following the power rule, bring your power to the front. So we will have negative 1 times with negative 2. Copy everything inside the bracket. So 3t squared minus 1. All power must be minus 1. We're going to get negative 2 here. And don't forget to differentiate what's inside the bracket. That's how you're going to get 60. So for derivative, once again, the differentiate of our function, we will get 12t divided by 3t squared minus 1 squared. Now for step number 2, we have to substitute this into our chain rule. So d squared y over dx squared will be equal to derivative of our first derivative. So 12t divided by 3t squared minus 1, the whole thing squared, times with dt over dx, in this case 1 over 3t squared minus 1. So our final answer here will be 12t divided by 3t squared minus 1 cube. Let's proceed with the last example. Now for this situation, we have a trigonal function. For x equation, we have sine of 1 minus 5t, and y equation is y equal to cos of 1 minus 5t. So we differentiate our x equation first. Dx over dt in this case would be derivative of sine would be cos of 1 minus 5t. Don't forget to differentiate what's inside the bracket. We're going to get negative 5 here. So our dx over dt here will be negative 5 cos of 1 minus 5t. Proceed to the second equation. Derivative of y would be dy over dt equal to, we differentiate cos, we're going to get negative sine of 1 minus 5t, and once again differentiate what's inside the bracket, we're going to get negative 5. So finally our dy over dt here would be 5 sine of 1 minus 5t. Substitute this into our chain rule, means that our dy over dx will be equal to 5 sine of 1 minus 5t times with 1 over negative 5 over cos of 1 minus 5t. Simplify this out, we're gonna get negative sine over cos can be simplified as tangent, so negative tangent of 1 minus 5t. Now we differentiate our dy dx once again, so basically d over dt of negative tangent of 1 minus 5t. Here we're gonna get derivative of tangent is basically secant squared 1 minus 5t, and once again don't forget to differentiate what's inside the bracket. We're gonna get negative 5. So this can be simplified as 5 secant squared of 1 minus 5t. Now let's substitute into the second derivative chain rule. So finally our d squared y over dx squared will be equal to 5 secant squared of 1 minus 5t times with our dt over dx, so 1 over negative 5 cos of 1 minus 5t. 5 can be cancelled out. 1 over cos is basically a secant, so this can be simplified as negative secant cube of 1 minus 5t.